Welcome, everyone, to this Professional Development Hour presentation brought to you proudly by the Atlanta Metro chapter of the Georgia Society of Professional Engineers, an affiliate of the National Society of Professional Engineers. Before we begin, we'd like to let you know that any opinions presented tonight are solely the opinions of the presenter and not that of the Georgia Society of Professional Engineers, the National Society of Professional Engineers, or any other of its affiliates. We certainly hope you will enjoy tonight's presentation, so sit back and relax. And on with the show.
Ready to get started here. Our presentation today. Before we get going, a good point, if you would remind you to please silence your phones. All right. Tonight's presentation is on the fundamentals of data centers. We hear all these, certainly the buzzword, and then you hear all the rumors and you hear all the innuendos. And so Farris, Shaheen, our speaker today, is here to demystify that and give us a straight scoop, as I say.
We got a lot of things to talk about. So there you go. Now you should.
Okay.
Sorry, I guess I turned it off.
You got it.
And then we're going to talk about the infrastructure in data centers, what they are, how do we cool, how do we power these loads, regular loads and AI loads, and what that looks like outside of the data center to a Georgia Power or to a water municipality. And then I think most of you know this, but we're going to spend a little time talking about some of the equipment that you see in a data center that is ever evolving over the last 5 years. There are pieces of equipment now that didn't exist that are commonplace in a data center. So we're going to run through that real quick. If you're not a consulting engineer, we're going to run through what codes are applicable for designing a data center. Also, special codes for special situations, lithium-ion batteries, and other things that we don't normally see anywhere else. And last but not least, we're going to talk about electrical and mechanical topologies for data centers and what the tier levels are for data centers and what you can expect to see. Like I said, if you have any questions, please feel free to ask as we go. Data center is basically a warehouse for computing, right? I did a lot of food processing facilities early in my career and cold storage facilities. So you have a cold storage facility where all your frozen goods, so they can get to you. You also have basically a computer warehouse where the conditions are such, the power is available so that you can get the information, or whoever can get the information out of that data center with little to no issue. So we have servers, we have storage devices, we have some fancy AI stuff that we'll talk about that are all distributed throughout the data center. Lots of cooling, lots of power, lots of water, lots of sewage is required, and that's where some of the communities voice their opinions. So we're going to talk about a normal data center, say file storage, low power, big footprint, and then we're going to touch a little bit on the changing to AI data centers, the different chips that they're using now, and why that affects what we're doing as engineers to cool and to provide power. Okay. Boy, that doesn't look very well. But so this is what a prototype typical data center looks like. Up at the top we have our mechanical yard. Based on what I see here, air-cooled chillers. And then below that we have the electrical yard with the generators and transformers. Below that it says UPS rooms, but basic electrical rooms that are serving the data halls. The green areas are the data halls themselves. That's just lines and lines of rack. And then the verticals there are equipment galleries. That's where, if we're air cooling, that's where the Cray units go, that's where the fan walls go. And that's where the power distribution units go to get power out to the data floor. So that is a pretty typical data center layout. And then we have office services on either end of the building. Pretty simple. Where do we want to put data centers, or where do companies want to put data centers? Where there's available power, right? There's available fiber to the site. There is, if you're going to be doing one of these 2 or 3 gig campuses, we're talking hundreds of acres, 200, 300 acres. It's hard to find those parcels anymore in areas that have the resources and the utilities to support those large data centers. And some other things, location of major highways. Some companies still do risk assessment. If you're near a military base, if you're near the airport, these introduce additional risk to the physical structure of the data center. Do you have a question?
It's more of a comment. I remember reading 20-some years ago that Google decided to go and locate a data center, and they decided to stick it up in one of the Nordic countries because it was cheaper for them to run the communication cables up there because the cooling was free.
Right. Yep, and that's something we're going to talk about. Climate. Where do you put a data center? There's advantages, maybe putting it up north in Canada. There are other advantages where there's more power available, maybe in a more southern location. And the other thing that we really don't touch here is where undersea fiber cables go is where the data centers cluster, right? So Northern Virginia, right? Washington, D.C. That was one of the first undersea cables, new undersea cables that was run from Europe over to here. So that's where the data centers started to be built, right? Low latency, available bandwidth. And over the years, as data centers became more and more profitable, we've got more and more lines coming from Asia, Europe, that are coming and developing areas where you're going to see more and more data center clusters. One other thing, a lot of states offer tax incentives to get data centers in their state. We're seeing that more and more go away as the states and the communities realize these massive data centers may only employ 15 or 20 people. They're not adding to the tax base. So you begin to see a little bit of a pullback on those incentives. And last but not least, data centers are now becoming a geopolitical hot potato. The war in the Middle East, data centers were being bombed to stop communications and stop have facility like we have here. And that reactor is what, 180 meg, 80 gig to 120 gig each reactor. You put a 3 meg load on an 3 gig load on an 80 gig power system, you're going to see a shift in voltage regulation. So utilities are getting more and more careful about who they add to their grid. I do a lot of work with clients that want to put a data center here, want to put a data center there. These days, if I want to get a 200 megawatt, a gigawatt commitment from a utility company, we basically have to do a full engineering study about the electrical load and the load print to prove to the utility that we're not going to affect their grid structure. Something I never thought we'd see 20 years ago.
Can you check the focus on that before you
It's just the display.
Oh. Anything else?
Yeah, I have a question. What are the characteristic water use efficiencies and power use efficiencies for some of these hyperscale units?
Give me about 15 minutes, we're going to cover that. And if I don't, ask the question again. Engineers love to quantify. So there's an organization called the Uptime Institute. They've developed a tier structure for data centers so that Microsoft can say, we have a tier 4 data center, and the industry knows what that is. Or we have a tier 3 data center. The industry knows what that is. I'll make these slides available to everybody. So don't write all this down. But basically, a tier 1 data center is the most basic data center. You have one path of power, you have one path of HVAC or cooling. That's it, no redundancies. In the old days, that was crypto mining, stuff like that. Today, with the reduced latency of fiber, some of the big players now are mirroring their data centers. They've got one in Reston, Virginia. They've got one in Oregon. And they're twins, they're parallel. Data goes here as well. So that their redundancy requirements on the infrastructure are lessened, because if one data center shuts down, the other one keeps running. And the client doesn't see any difference.
It's probably easier to keep up than all that redundancy of one campus. I mean, if you're trying to so yeah, so I guess it's easier to try to have redundancy in utilities, one location. It's just easier to have separate, instead of doubling the size in one location and having, if the utilities go down there, that makes sense.
It does, but some clients, it depends on the client's wishes, right? Now, if you're an Amazon and you're running your Amazon business, not the web services, but your business, if you've got somebody searching on Amazon for tennis shoes and there's a glitch and they have to press that button again to reload the tennis shoes to look at them, no big deal. The minute you put those tennis shoes in your cart It goes to a higher tier data center with more security around it and encryption around it. Number one, to protect your data, but number two, you've got money in the cart. They want you to finish the transaction, and they're going to do anything they can not to do that. Yes, sir?
Is there an optimal size to a data center? Have you been able to reach something that is the most economical in all variables?
These days, in the 200 megawatt range, I'm seeing data halls in the 120 to 300,000 square feet. It just depends on the density of the rack, the power that's available. So it really depends. I worked on a project, I guess about a year ago, where they were putting in 2 racks side by side. The rack itself was 2 megawatts of load. That was something completely different. We had to do different things around that, and we'll talk about that later. But the way that data centers are going to evolve is changing quite a bit. Data center 2 has, tier 2 has some redundancy. Tier 3, the big deal here is concurrent maintainability, right? So if I've got 20 chillers serving a data hall, one of those chillers goes down or needs to have maintenance, I don't want to diminish my capacity for my data center. So having concurrent maintainability means you can take any piece of the infrastructure out, whether it's cray units, pumps, switchgear, and not affect the end load and operation of the data center. And then tier 4, what that adds is fault tolerance. It's designed in such a way if there's a fault in a certain area, it's going to be contained in that area and is not going to spread through the rest of the data center. So, questions on the tier system? Okay. I apologize for the slide, but this is the stuff that goes in the racks in the data center. I'm not sure if everybody knows, we've got network switches, we have local firewalls protecting this rack, we have traditional routers, we have storage, we have computer storage, computer servers, we have a thing called a power distribution unit. This is at the rack where we feed the rack and it takes the power and distributes it to all these pieces of equipment. Some racks today have a UPS inside the rack, depending on the client's technology preference. And one thing that you wouldn't think would be important is blank panels. They're very important in a data center if you're going to be doing a HAC, which is hot aisle containment, because that allows that directs the airflow to the proper areas within the rack.
So, Farris, how, I guess like, I'm just looking at the rack now. I just kind of like, in general, how much like open, like blank panels would you, like ideally?
It depends on the client and the density, kind of out of my area of expertise. But I've seen racks completely full. I've seen racks with a couple of servers in them and that's it. And then we're going to talk a little bit later about what we see in AI distribution that kind of blows this stuff out of the water. There we go. How is AI changing data centers? Any ideas? Yeah, they want to eat more, right? They want more infrastructure. So, what is causing this? There has to be a technology change within the servers that's allowing this to happen. So, everybody know what a CPU is? Right? Central processing unit that's in your PC at home or your Mac at home. Those things are great. They can do math. They're the computer's brain. They like serial calculations, one at a time. We're not going to do any more than that. You're going to have to wait. Now, in truth, there are some recent CPUs where instead of having just one core, they may have 2 or 3 cores, which speeds up processing. But the game changer with AI is the GPU. You guys heard of that? Right? So what's neat about the GPU is it has multiple cores on that chip. So it can do parallel processing. It can do many different actions at the same time. Where a CPU typically is about 100 watts, a GPU is a 600 watt draw. Okay? Big deal, 600 watts. But when you have a server that has 4,000 of these chips on it, you begin to see how it snowballs and becomes a bigger load. So, and this looks terrible as well, but I want to show it to you. This is a GPU chip firing. So, everybody hold their left hand out. Okay, you see this? That's 170% current of the GPU as the GPU fires. Within milliseconds, it drops down to 100% load. It'll run that 100% load as long as it's needed, and then the GPU fires off, goes to 30% until it's needed again. We don't want to design electrical systems for 170% of the load of the chip. My owner doesn't want to pay that, right? So there are ways that we're addressing that AI load now that's different, but it doesn't change the fact that the densities are getting higher and higher. This is from a UPS manufacturer. This is the standard curve that they use to test, in this case, UPSs, on how they handle this type of load. The red is a millisecond going up to the 165, 170. Then we go down to approximately 150 degrees for a few more milliseconds. And then we reach a steady state, which is the 100% to 90%, and then drop down to a 30% load. So this is a more binary approach to the curve. Measurements were taken with an AI load on a UPS. The top one's the current, the kVA. You can see it going up and down based on when the GPU chip is firing. Oh, and another great thing about GPU chips, if they're in the same rack or the same pod, they kind of get a kick out of syncing together. So you're going to see not one do it here, one do it here, but you're going to see a pulse that's going to appear on your UPS out back to the UPS output. So that's the power fluctuation, that's the current fluctuation, and as we would expect, the voltage is pretty much steady.
What does GPU stand for?
Graphic Processing Unit. So if you want to take it a step further, I don't know, 10, 20 years down the road, the structure of a GPU chip is going to be very similar to a quantum computer. What's great about a quantum computer? Infinite parallel paths for data to be calculated. The only thing we haven't done yet is been able to provide a stable environment for quantum computing. This is kind of the going from middle school to junior high with these GPUs. And then, well, I can talk a whole lot about quantum computing. So how do we address this? Most manufacturers, UPS manufacturers, have a setting that can be changed where it allows when the UPS is, the rack is asking for too much power, it allows the UPS batteries to discharge to cap that power. An example, lithium-ion batteries, 10-year lifespan. They're expecting maybe that go to 9 or 8 years, but it's a much less expensive way to deal with that surge than building a larger infrastructure, electrical infrastructure, or trying to handle this at the medium voltage level, which would entail a BESS system, some fancy controls, and it's still not proven that that type of system will react fast enough to assist the UPSs. So right now, this is the easy button for AI loads. Questions?
I was thinking about all the e-waste and kind of recycling. Can you speak to that? Will you talk about that later?
I'll talk a little bit about it now.
Yeah, I'm just curious. Like, man, this is,
So,
everything has a lifespan. So.
Right. So, specifically over the past 5 years, there's been a couple of companies that are developing reclamation and recycling of lithium batteries that with very high heat and very high pressure that can extract the lithium. They basically burn everything else off the chip off the battery but the lithium. They can scrape that lithium, recondition it, and put it in another battery. That's not very commonplace now, but that's one of the technologies that might change that. And then there's also there's all kinds of other battery technologies that are out there. So we're going to eventually get to a battery chemistry where it's not bad for the environment or all these other things. Real quickly, yes?
One of the technologies that I've heard a little bit about is that instead of actually going and recycling the batteries in that manner, tearing them apart, is that they take old batteries from electric cars that have lost some of their capacity, turn them into BESS, battery electric storage systems, or using them at data centers. So they don't have to go and tear them apart, they just use them as is.
I have not seen that with my clients. That doesn't mean it doesn't happen, right? Most clients, they want a product that has a warranty and they can get to mitigate some of their risks. Okay, so what do we need to know? We're designing mechanical indoor conditions, humidity, what temperature do we want, what humidity do we want in the data center, and typical equipment that does this are chillers, air handling units, cracks, fan walls. So, and controls and monitoring can get very difficult depending on how the client wants to control his system. Okay, let's talk about cooling technologies. This is going to come into the play with water and the community. So basically there's two types of cooling systems that are used in data centers: open loop data centers and closed loop data centers. Open loop data centers are the traditional centrifugal cooling towers. The water flows and the cooling tower through evaporation cools the gas or the liquid at that time. Evaporation is it's a lot, and we'll go to the numbers in a minute. A closed loop system is a system that the heat from the liquid that's coming from the data center expels its heat through air, not a liquid medium. So instead of, well, we'll look at the numbers. So basically it uses zero water for a closed loop chiller system. Yeah, we're going to talk a little bit about thermal storage. What does that do in a cooling system for a data center? And a very brief overview of CFD modeling, which allows the engineer and the owner to place equipment in such a way that it maximizes its performance. Okay, I think we've talked about this, what's in a data center and the equipment that's there. Oh boy. Okay, so let's do we did a little study, case study for a 200 megawatt data center. The first thing is there are humidity requirements in a data center. So depending on the client, there's a range of allowable humidity. Usually it's 25 to 35% relative humidity. So in the data center environment, that means that we need humidification. So for a 200 megawatt data center with the design basis here, just to humidify the air in that 200 megawatt data center is going to use close to 200,000 gallons of water a year. Okay? Sounds like a lot.
Is that per day? 200,000 gallons.
That's per year. Peak use is 2,200 gallons a day. Average use is, I think, around 600 gallons a day. It just depends on the external conditions. Yes, sir.
I heard on the news today that the studies on the amount of water that they used were grossly exaggerated at like 100,000%.
I hope my engineers aren't doing that.
At any rate, that was the announcement today, that the original basic studies that everybody's been relying on were inaccurate. You really haven't heard about it?
Apparently not. Should I just skip this section? So anyway, so we've got a base 200,000 gallons a year just for humidification. And in our study here, we did a traditional air-cooled chiller system where the refrigerant comes back into the chiller, fans blow air over the coils, and that removes the heat from the liquid. It's a closed loop, there's no evaporation. 0 gallons a year for an air-cooled chiller system. Oh boy, sorry guys. So, and the other option we looked at for the client was a water-cooled chillers with the adiabatic dry coolers. They're the latest in dry coolers. Open loop, based on our calculations. 15,500,000 gallons of water a year just through evaporation. So if I'm running a municipal water system, I'm kind of pushing for the air-cooled stuff, right? And that's a concern, that educated consumers and voters are learning, and they want answers to those questions. Okay, let's go over here. So this is an isometric of, we'll call it a workspace module, white space module, we'll call it a HAC, hot aisle containment. And owners are getting these fabricated and built and just delivered to the site, right? So we've got structure all the way around and above that supports not only power but cooling to the chip and cable trays for fiber and communication.
Is that, you say hot aisle?
Hot aisle, yeah.
You say hot aisle containment, is that referring more to just the heat that puts out, or is that like when the fire breaks out, does that provide some containment?
No, it's specifically, you can do hot aisle containment where you, and I have a slide of this later, where you run air through the front of the servers up to the back. The racks are on either side, and then the heat rises and is taken back to the chiller. The other one's cold aisle containment, where the general data center is hot, 85, 90 degrees, and you contain the cold air, force it down so it blows the other way through the servers and cools them. A lot of this stuff is prefab. The stuff here is the racks. The racks on the other side, the front of the racks. You see we have sliding glass doors, and above the racks, that will typically run up and go to a either an acoustic type ceiling to allow the air to get back to the crays, or it will at some point be ducted back to the crays.
Are ammonia chillers coming?
Or what?
Ammonia chillers.
Yes, what about them?
Are they often used in data centers?
No. It's been my experience 25 years ago when I did a lot of cold storage, food processing, ammonia refrigeration was the king. Over the years, due to concerns about the hazardous effect of ammonia and technological breakthroughs in traditional cooling techniques, ammonia refrigeration is not really used unless it's a research facility or it has some very strange cooling requirements. So, I haven't seen it in a data center ever. So this is, again, the hot aisle containment. We've got our cray blowing through the racks, goes up and over and back into the cray to dissipate heat. That's probably the most, that's what I see most in data centers today is hot aisle containment. Okay, that AI white space module, or HAC. So we're looking at one set of racks. There's another set of racks on the other side. These different colors are different bus ducts that feed the rack and the equipment in the rack. These are 800 amp bus ducts. They're each fed from a different system. So at the rack we have approximately two in redundancy. But this rack that one rack is basically to serve a 2 megawatt load. Yes, sir.
What sort of voltage?
We're going to get to that. So typically 208's been used, 4-wire. 415 4-wire is very common now. I don't see a lot of 480.
Is it 450? Is it 450?
415.
Oh, 415.
Yeah, 415, 240. And I've been reading articles about the development of an 800 volt DC system that could be deployed, because what do servers run on? They run on DC. So the theory is, why introduce heat into the data hall when we can do that conversion somewhere else and eliminate it? But that's new. People are working on it. I haven't seen it used successfully. Okay, so that's the section view. We got one side and the same thing on the other side. Just real quickly, there's the bus duct again, and this is a section on either end. And then we see pipe connections here. That's chill water supply, chill water return that is coming from the process or the factory water system. We'll talk about that in a little bit. That's different than the liquid that's cooling the air. So we talked, and there's this new piece of equipment called a CDU, a coolant distribution unit. So what typically happens is these little CDUs are placed in the gallery beside the fan walls or the crays and the PDUs. And you know, they're little things about like this. And they take the chilled liquid and squeeze down the envelope, the tolerance of the flow of the water, the temperature of the water. Because if you're going to be cooling direct to chip, there's a lot more stringent requirements. So they require a separate water system, technology, cooling system, whatever you want to call it. And so where I showed you the rack and the cooling, the pipes going in and out on the side, that would be coming from a CDU. That's kind of the new wrinkle these days in cooling for a high density data centers. We talked about codes a little bit. We use the same building codes. They're basically based on model codes. Some states change, may pass amendments to make the code a little more stringent in certain areas. NFPA has, I think most of you are probably familiar with NFPA. They have standards for pretty much everything hazardous that's going on in a building. And then there are other standards, Factory Mutual. They're basically an insurance company, but they have rules and regulations that they want to impose on their clients to lower their risk in constructing a building. We talked about the Uptime Institute. You can get your data center certified by the Uptime Institute if you want, so you can have a plaque on the wall that says what tier it is. A lot of people don't do that anymore. And with new battery technologies, there are a couple of IEEE standards that come into play now in data centers where they really don't come into play in other building types. So the code is always changing and usually gets added to. Whoop, sorry guys. Okay, let's talk. Go ahead.
Question. Just curious if waste heat is being used to kind of get back to the power demand of data centers anywhere.
It can be done. Traditionally, other than generating power back to the grid, there's really no other use for that heat. I'm working on a facility that is adjacent to a power generation facility, 150 megawatt, 200 megawatt generation facility, natural gas turbines. So we could take the heat off the turbines, run them through absorption chillers and get some cooling out of that. But it typically hasn't proven to be very efficient. Okay, so, yes, sir.
Let's get back to the power use efficiency and water use efficiency for the data centers.
Yes, sir.
How efficient are they? I've seen numbers that say 1.8 cubic meters of water per megawatt data center. That's a standard number.
1.8 cubic meters
Of water evaporated.
in a day, in a month, in a year.
That's per kilowatt, per megawatt.
Okay.
So that would be presumably times 24.
Okay. I have never done a study like that. It could very well be true.
The other thing is, what is the power use efficiency? It's how much, let's say you had a 200 megawatt facility.
Mm-hmm.
What's the heat level?
Okay, so there, and we'll get to this in a minute. There's a PUE calculation that is used as a measuring stick for efficiencies of data centers. That is the total load of the data center divided by the IT load of the data center. So it's typically a number greater. It is a number greater than 1. If the higher it goes, 1.2, 1.5, 1.8 is a less efficient data center. Now the efficiency of the data center really is determined by a bunch of different things, the type of lighting that's used, control systems that are on board, whether you use, if you want to use an open loop system, it'll give you a lower PEU than a closed loop system. So there's not one right answer to a client, right? Did that help? Typically in a IT block, an IT equipment load, typically see about 6 to 8% losses in the entire distribution system. Again, based on the efficiencies of transformers and UPSs and other things. But those losses need to be taken into account when we're designing the cooling system as well. So it's, uh-oh, what did I do?
Your screen's still on?
Is diseconomy of scale a real thing?
Yes.
Where do you know the point?
Huh?
How do you know if you reach the diseconomy of scale?
Well, the profitability of hyperscalers will tell us immediately. Yearly I go to a presentation on the data center in the economy, what we see looking back and what we see looking forward. I know of one colo provider that is in financial trouble.
What?
I know one colo provider that is in financial trouble. Other than that, the colocation people, the hyperscale people, they're building the new data centers on the money that they're making off of their old data centers.
So some of this stuff is being, shall we say, built on spec?
Yeah.
Okay. They don't, it isn't, say, Joe's Pizza wants a data center and, no, they'll build and hope the Joes will
Yes.
sign the contract. Oh, this is...
Right. Right. So, did that answer? Okay. So, when we're talking about a data center, there's a number that's called N. N is the IT load of the data center. That's the computer load in a data hall. That can be a megawatt, that can be 500 kW. And then from that, we build on topology that meets the requirements of the client. This is typically an enterprise topology where we have an A-side electrical system, a B-side electrical system. Either side can carry the total load of the building. They stay separate with the exception of a tiebreaker where if one fails, the entire load of the building is switched to the other service. Very reliable, very resilient, very expensive. Okay? And again, even today in enterprise data centers, you'll see this deployed. Another topology is an N+1 block redundant topology. So you see all the colored blocks. Ignore the gray one over here. All of these blocks are, let's say, 3 megawatt IT blocks. So in this system, we have 6 IT blocks, and the gray one is a reserve block. So what happens is if one of these blocks fails, the reserve block automatically picks it up. The only time that becomes an issue if you have 2 blocks fail at the same time, you have to do some other things with the infrastructure and the wiring on the floor to make sure that you keep your servers running differently. But this is much more cost effective than a 2-in system.
What's the usual failure mode?
Tell me a little more.
What is the usual failure mode? You talked about a unit failing.
It varies from data center to data center. There are things that can be done that are reliability studies that use calculus, differential equations, and stuff I've long forgotten, based on the equipment type, where it's in the system, a statistical analysis done, and can give you failure rates for each specific piece of equipment. What the Uptime Institute tier system does is it gives you estimated reliability, downtime percentages, based on the topologies that they're recommending for each system. So a tier 3 data center is 99.999 typically. Tier 4 is 99.9999, an extra 9. So, and then at that point, the occupant or the owner makes a decision based on finance, what SLA contracts they have out, as to what they're willing to live with. Nothing's 100%. And one other little system here is a distributed redundant system. We have 4 systems. One of the systems goes down, 2 of the systems go down. Through downstream controls, we can still keep 60 to 70% of the servers intact. So with that, as one audience member is leaving, I'm done. Are there any other questions?
Talked about the closed loop cooling versus the open loop, which uses water. Is there a rule of thumb to say that what the total cost of one versus the other? I think the closed loop are probably more expensive.
Actually, no.
Really?
Actually, no.
Water and electricity.
The open loop system is more expensive. It's a different type of compressor. You have a completely separate piece of equipment that's distributing heat. So that's 2 pieces of equipment versus 1. And over the last 10 years, technology of air-cooled chillers, where they were 250, 300 ton, now we can get air-cooled chillers that are 800 ton. So upfront cost for air-cooled is cheaper. Open loop, more expensive. But you can get a PUE of about 1.5 with an air-cooled chiller system. But with a water-cooled system, you can get to 1.2, 1.25, 1.3 PEU. So then it becomes a math exercise as to whether the client wants to put money up front or maybe not do that. Oh, and I think we talked about this, but I'm seeing a lot of big cloud people looking at on-site generation, whether that be through natural gas turbines or other methods, through even diesel generation or natural gas generators. I do know that there are a couple of modular nuclear systems that have been attested, and they're trying to get approval for those. And I would say somewhere in the next 5 or 10 years, you may see a data center built out in the middle of nowhere, and they just plop in a couple of 100 megawatt reactors in series and power the data center. But that's all pie in the sky stuff. That's why I'm still doing this at my age, is because I dig the technology changes.
Tonight on the news, on the radio, there was talk about a company that wants to put data centers in orbit.
Certainly have power. We got a lot of solar power. How are you going to cool the data center? My first question would be, how are you going to get water up there? And how are you? I would imagine it has to be a closed loop, but it's possible. There have been studies where they've put data centers under the sea, using tidal currents to generate electricity and cooling, and the cooler waters below the ocean. I've seen one or two studies on that. It really hadn't gone further. So I bet you we'll have men on the moon again before we have a data center in space.
It'd be particularly hard to get a serviceman to go up there and fix it.
Yeah. It's like they didn't get a plumber up to fix the toilet. The astronauts had to do it, right?
All right, folks, if there are no questions, big round of applause.
Thank you.
This meeting tonight was posted, information about it was posted on our LinkedIn site, LinkedIn company site.
Oh, thank you so much. It was really a pleasure.
Raise your hand. What
I enjoyed this.
Would you put on the site about tonight?
Far cry. When I first graduated from Georgia Tech, even though I was an electrical engineer, my first job was selling computer room air conditioners and power backup.
And when nobody needed them, right?
to whole floors, sell to the IRS, Bank of America, and all that stuff. And the complexity of the requirements compared to this thing, it's just been, if you had to guess how much you saved.
What we have planned for the next
Well, Joe Powell he's a supplier. He's a manufacturer's rep. 30 years ago, he started carrying this Liebert line.
Chemical engineering.
And it was like, what the hell? Nobody needs this. And now that Liebert line has turned into a multi-billion-dollar corporation, and Joe's been able to represent them all the way through. It's luck of the draw.
They were my competitors.
We hope you enjoyed this presentation given at one of the Atlanta Metro Chapter meetings of the Georgia Society of Professional Engineers, an affiliate of the National Society of Professional Engineers. To find out more about us or to join us, check us out at gspe.org.